In this module, we will discuss framing of likelihood function and the maximum likelihood estimation in the context of survival data. Now, survival data usually come from life testing experimentation, different clinical trials, etc. The most common feature of survival data is censoring. So, due to censoring, we have to pay special attention while framing the likelihood function, obviously based on survival data. In this module, we will study to frame the likelihood function and to discuss the maximum likelihood estimation under type 1 and type 2 censoring. Censoring in particular is a key issue in survival analysis. It is censoring which distinguishes survival analysis from regular statistical problems. Censoring is when an observation is incomplete due to some random cause. The cause of the censoring is usually dependent on the event of interest. In this module, that is why we will study the maximum likelihood estimation under survival data in presence of type 1 and type 2 censoring. Censoring differs from truncation in that the incomplete nature of the observations in truncation occurs due to a systematic selection process inherent to the study design. Based on the directions through which incompleteness in the observations comes, censoring is of three types: right censoring, left censoring and interval censoring. Right censoring. It is the most common form of censoring. Here, the lifetime of an item is followed until some time at which the event, that is failure or death, is yet to occur, but the event takes no further part in the study after that time. As per example, a lung cancer patient is recruited for clinical trial to test the effect of a drug on his survival from lung cancer. But suppose he dies in a car accident after T years of his lung cancer discovery. This implies his survival with lung cancer is at least T years, but exact years cannot be known. So, clearly it is a right censored situation. Left censoring. This occurs when the event of interest has already taken place at the time of observation, but the exact time of occurrence of the event is not known. For example, onset of an asymptomatic illness like brain cancer or infection with a sexually transmitted disease like HIV or AIDS. Interval censoring. Here, the exact time of event occurs is not known precisely, but an interval bounding this time is known. In case the interval is too short, say for example 1 day or 1 hour, etc., the common practice is to ignore the interval censoring and to set one endpoint of the interval consistently. For example, failure of a machine during Chinese New Year celebration, which takes place throughout 15 days, or infection with a sexually transmitted disease like HIV or AIDS in between 2 annual checkups. Depending on how censoring mechanism will work, there are 3 broad types of censoring: type 2 censoring, type 1 censoring and random censoring. Now we will discuss briefly each of these three types of censoring in the form of right censoring, and also the maximum likelihood estimations of the corresponding parameters associated with the survivorship probability models. Type 2 censoring. Suppose n random sample units are set on life testing experimentation, but due to some reasons the experiment terminates after consideration of smallest r readings where r is necessarily less than n. Let this be denoted by the order statistics t order 1, t order 2, etc. up to t order r. Here integer r is non-random and prefixed to be decided prior to the experiment. And since the remaining n minus r random sample values are at least as high as t order r, this implies the sampling scheme is a censored one. Such a censoring is known as type 2 censoring. Type 2 censoring are frequently used in life testing experiments. Here, say total of n items are placed on test. Now, instead continuing until all n items get spared, suppose the experimenter waits just for the first r failures. Such test can save both time and money. Let capital Ti denote lifetime or failure time of ith item. Suppose Ti's be IID having a continuous distribution with PDF small f t theta and CDF capital F t theta at the point t, where theta denotes the parameter of the distribution. Then given small t order 1, small t order 2, etc., small t order r, which are the realizations of capital T order 1, capital T order 2 up to capital T order r. The likelihood function of theta under type 2 censoring is capital L theta equal to n factorial by n minus r factorial times product of f theta t order 1, etc. up to f theta t order r into capital F bar theta t order r whole to the power n minus r, where capital F bar is the complement of capital F, that is 1 minus capital F. Verification of this likelihood. We know from theory of order statistics that the joint PDF of all the order statistics t order 1, t order 2 up to t order n is, say, small h theta at the point t order 1, t order 2 up to t order n, and that must be equal to n factorial times product over I from 1 to n PDF small f theta at t order I. This implies the marginal joint PDF of t order 1, t order 2 up to t order r at the point small t order 1 dot dot up to small t order r will be g theta at t order 1 up to t order r, and that can be obtained by integrating n factorial into product over f theta ti with respect to t order r plus 1 up to t order n, and that is equal to n factorial into product over I from 1 to r f theta ti times integration with respect to t order 1, etc. up to t order n of the PDF f theta t order 1, t order 2 up to t order n, and that is equal to n factorial times product over I from 1 to r f theta t order I times integration of the PDF f theta t order n with respect to t order n, and the dependent range should be taken as t order n minus 1 to infinity. Now this integration will give us 1 minus capital F theta at t order n minus 1. Again taking the corresponding PDF, that is f theta t order n minus 1 with this form and integrating it with the dependent range t order n minus 2 to infinity, we get on simplification that n factorial times product over I from 1 to r f theta t order I times integration of 1 minus f theta t n minus 2 whole to the power 2 by 2 factorial, and we can draw the PDF f theta at t order n minus 2 with this form, and we can again integrate it such that we can get n factorial by 2 factorial into 3 into product over I from 1 to r f theta ti and integration of 1 minus f theta t order n minus 3 whole to the power 3 multiplied with small f theta t order n minus 3 and the other PDFs as it is. Now proceeding this way and noting the symmetry in each stage, we can finally get that g theta of t order 1, t order 2, t order r equal to n factorial by n minus r factorial times product over I from 1 to r f theta t order I times f bar theta t order r whole to the power n minus r. But we know that given the realizations, the form of joint PDF serves as the likelihood of theta. Hence, the form of the likelihood is verified. Here, capital F bar theta at the point t is the survival function at the time point small t. Now, let us consider the following illustration. Let the lifetime of an item follow an exponential distribution with mean theta. This implies the PDF is f theta t equal to 1 by theta into e to the power minus t by theta, and the survival function at the point t is f bar t theta, that is equal to e to the power minus t by theta. This implies under type 2 censoring, the likelihood function of theta will be capital L theta equal to n factorial by n minus r factorial times 1 by theta to the power r times e to the power minus t order 1 by theta etc. into e to the power minus t order r by theta into e to the power minus n minus r into t order r by theta. On simplification, we get this is equal to n factorial by n minus r factorial times 1 by theta to the power r times e to the power minus summation I from 1 to r t order I plus n minus r times t order r whole divided by theta. So this implies the log likelihood small l theta will be constant minus r times log theta minus summation ti plus n minus r times t order r divided by theta. This means the first order derivative of small l theta, that is l prime theta, will be equal to minus r by theta plus summation t order I plus n minus r times t order r divided by theta square. This implies the unique solution of likelihood equation L prime theta equal to 0 will be theta hat equal to summation I from 1 to r t order I plus n minus r times t order r whole divided by r. From second order condition, we can ensure that this theta hat maximizes the likelihood function capital L theta. That is, this theta hat is the maximum likelihood estimator of theta under type 2 censoring. Next, we discuss type 1 censoring. Type 1 censoring. Sometimes experiments are run over a fixed period of time such that the exact lifetime of an item will be known only if it is less than some predetermined value. In such a situation, the data are said to be type 1 censored from right. More precisely, a type 1 censored sample is one that arises when n items numbered say 1, 2 up to n are subject to limited periods of observations, and let capital L1, capital L2 dot dot up to capital Ln be those periods such that ith item's lifetime denoted by capital TI is observable only if capital TI is less than equal to capital LI. Here capital LI is called fixed censoring time for the ith item. If all LIs are equal, the data are said to be single type 1 censored. Let us assume that capital TIs are independently and identically distributed with common PDF small f theta t and survival function capital F bar theta t. From ith item, we record the exact lifetime capital TI as the realization provided capital TI is less than equal to capital LI. Otherwise, capital LI is recorded as the realization. Let capital Y denote the potential response, that is the response which is surely obtained from ith item. Then we can easily say that capital Y is equal to capital TI if capital TI is less than equal to capital LI, and this is called uncensored case. Similarly, capital Y will take the form capital LI provided capital TI is greater than capital LI, and this situation is called censored case for all I. This implies Yi takes the minimum of Ti and Li. Also define indicator variables delta I which takes the value 1 under uncensored case, that is when Ti is less than equal to Li, and delta I equal to 0 under censored case, that is when Ti is greater than Li. Then these delta I's are called censoring indicators. So the type 1 censored data can be represented by the pairs of random variables capital Yi delta I for all I. This implies the joint likelihood of theta for given data set, say small ti comma delta I for all I from 1 to n, based on the paired random variables capital Yi delta I's will be capital L theta equal to small f theta Ti whole to the power delta I into capital F bar theta at the point capital Li whole to the power 1 by delta I. Now the question is how this is obtained. It is true that probability that capital Yi takes the value small yi given delta I equal to 0 must be equal to 1 provided small yi is equal to capital Li. It is because of the fact that delta I equal to 0 is equivalent to saying capital Ti greater than Li, and that is equivalent to saying Yi equal to Li. Or we can say that probability that Yi equal to small yi comma delta I equal to 0 is equal to probability that delta I equal to 0, and that is same as saying probability that Ti greater than Li provided small yi equal to Li. Now this is nothing but capital F bar theta at the point small yi when yi equal to capital Li, that is when delta I equal to 0. Or we can say that the likelihood corresponding to ith item is capital Li theta, and that is equal to capital F bar theta at the point small yi if delta I equal to 0 or equivalently if yi equal to capital Li. Let us denote this relation by star. In this module, we discussed briefly about the general notion of censoring. We also studied how to frame the likelihood function and how to study the maximum likelihood estimation with survival data under type 1 and type 2 censoring. An illustration helped us towards this discussion in this context.